Okay, so sorry for the delay. So only one beamer working today. I'm not sure what happened to the other one. So actually both should be working, but only one is working today. I'm sorry. Let's see for the next time. Okay, so today we want to end up with the chapter on transactions, recovery, and concurrency. And today it's about how can we can we do it on the hardware side, like do all the locking that to allow concurrency. Okay, so last time we talked about the two-phase locking. So that ensures which are the properties of the 2PL. What kind of schedules does 2PL guarantees you? You remember, so we had the different properties last time, like we had recoverability here, recoverability, avoiding cascading aborts, strict schedules, and another property was about serializable schedules. And now the question was, if we have a history, a schedule which has been gone through the 2PL, in which part of it is it here? So we ended up last time and said, okay, so there was 2PL and we had the strict 2PL. 2PL. And what does the strict 2PL ensure? So both ensure serializability. And what was the difference between those two? Yeah?
I'm not sure, but I think maybe the one actually ensures strictness, because
of course.
Strict, and the other one does just ensure the recoverability.
Exactly, that's how it is. So here is the 2PL, and here is the strict 2PL. So this part, no, it's not. So this part, like all the strict, not all, but all the 2PL are with, so strict 2PL ensures strictness and serializability, and the normal two-phase locking ensures recoverability at least. Okay, so we ended up with that, and the idea is, okay, for having the two-phase locking, what do we need? We need locks. And now the question is, what happens if there's more than one transaction which wants, if there's more than one transaction who wants to claim a lock? And okay, the idea is, there are some slides on the hardware side, how actually are the locks implemented. So the idea is, okay, we have a big hash table, and every transaction has a lock, and each lock, so we have, like here, the data items, like here the data item A, B, C, D, and so on. And we say, okay, every transaction acquires a lock, for example, a shared lock. So if there's more than one, we have a shared lock. And yeah, and every transaction holds more than one lock, for example, on different tuple D, E, F, G, H. Okay, so that's how internally the locks are implemented. Okay, so traditional architecture, one mutex per lock chain, within lock, separate locking waiting mechanism, and the idea is, okay, we just have locks like you learn in programming. And the idea is whether we can do this more fine, the granularity we have. Do we need to lock for everything, or can we just lock single items? And the idea is, how can we reduce the lock sizes? So typically we have 64 bytes per lock, and then we say, okay, use less locks, so have a smaller granularity. And the idea to reduce the size is called multi-granularity locking. So here again, standard locks contain a wait mechanism, and yeah. So let's start with deadlocks. So again, we have two transactions, And the idea is, okay, we have two data items. We have data item 1, B and A. And we see we have a exclusive lock. Something makes a noise here. I'm not sure what it is. But as soon as I'm writing here, I hear a strange... Okay, so here we have an exclusive lock. Exclusive means writing. Okay, so we have T1 acquires a lock, and then T2 acquires a lock B, and then we have again, okay, T1 wants also a lock, an exclusive lock on B. But as we know, the compatibility matrix with shared and exclusive locks. So this is the lock already hold, and this is the lock we want to have. So shared locks are compatible with no locking, and exclusive lock are only compatible if there's no lock. So we see there's already a shared lock. We want to have an exclusive lock. Exclusive and shared lock are not compatible, so we can see T1 is waiting for T2. And then T2 wants a shared lock on A, but currently T1 is holding a lock, so we have another dependency. So this is called the wait for graph. So, do you remember the serializability graph, which is about conflicting write operations? What is the dependency between wait for graphs and serializability graphs? No, that's not the case. So if we draw a serializability graph, we have first the T1. So because here we have a write, so actually after a lock should also come at least a read of A, and here there must be a write of B normally. So here we have first the write, and then afterwards the read. So we would have here another dependency, and then we see T2 reads B before T1 writes it, so we have another dependency. So actually it's the same. So we have, so they're not the same, but we also have a circle here. So it would be visible if we would add a third transaction. For example, if we have a third transaction, the third transaction, what maybe it wants also access on B, for example. So then in the wait for graph, T3 waits on B, which depends on both, so T1 and T2. But then here, what's the order? When does T3 comes? Afterwards. So we see first T1, A, then the A here, and the B here, then the B here. So basically T3 has to come afterwards. And now it's obvious what's the relationship between a wait for graph and a serializability graph. So this is the serializability graph here, and this is the wait for graph. Yes?
Is it like the inverted one?
Yeah, it's just the same errors, but just inverted. So that's the relationship between the wait for graph when we are talking about blocks, and the serializability graph is when it's about the serializability property. Yeah, so actually that's the relationship between both. Okay, so now you have seen a wait for graph, and what do you see also? If we, as soon as we have a cycle, we have a deadlock. So T1 is waiting for T2, and T2 is waiting for T1. So now the question is, how can we find deadlocks? And so yeah, so the idea is, okay, no transaction should be wait forever, would be sad because the transaction would never come to a result. So two possibilities. So either you can use timeouts, so you can say for the transaction, okay, after a certain time I just abort. So the transaction says after a certain amount of time the transaction decides to abort. but the question is when to abort. If we have a long-running transaction, it might depend just because on a long computation, so a time-expensive computation, but not because of deadlock. So you have to make the trade-off between whether it's a deadlock because the transaction cannot acquire a lock, and whether the transaction is compute intensive. So it's hard to find a good timeout for killing the transaction. And the other ideas, as I have shown you, the weights 4 graph. And in the previous example we only had 3 nodes, and here we have 5 nodes. Okay, so you see 2 cycles, like here's the first cycle and here's the other cycle. And now the idea is, okay, which transaction should be killed to eliminate any deadlock? For example, yes. So if we kill T2, T5 can get all the resources it needs, and also T1, and all the dependabilities are resolved. So so the idea is, okay, you create a weights 4 graph, and then you know which transaction to kill. What else could be done to avoid deadlocks? You mean a serial execution? Of course, serial executions are always possible, yeah, but serial executions are expensive. Anything else? So depending on the lock order. You have seen here, the lock order T1 acquires all the first lock, then the second one. What else could be done? Yes? No, it's not a
transaction which started first to get all.
Yes. So actually you say at the beginning claim all the locks. Yes. That's actually what I want to see. So actually just pre-claiming. So we have still the two-phase commit protocol. So here again we have pre-claiming is actually a variant of the strict two-phase locking. Two-phase, that's an L, not a C. So if you get confused. So two-phase locking, strict two-phase locking. So actually we have the growing phase, but actually the growing phase is instead atomic. So the normal growing phase is here atomic, and then we have the shrinking phase again. But again, in strict two-phase locking, this shrinking phase is also atomic. So basically it's just here shrinking and here growing. So the idea is, okay, the transaction is only allowed to start if the transaction has all the locks. But actually this means, okay, try and error, we have to try it again and again and again. And as soon as there are competing transactions, this means we have always one winner, one loser, and therefore it's not feasible in practice. Okay, so now I want to go through different possibilities. So one idea is of timeouts, then I have an algorithm for deadlock detection, and then I want to show you optimistic synchronization. So basically, as soon as we have locking, it's all pessimistic. Locking is like, okay, gain all the informations beforehand, all the resources. So locking is always pessimistic, and saying, okay, let's do it without locks is optimistic. So I will show you first all the pessimistic approaches, and finally I want to show you all the optimistic approaches. And like here, I have an algorithm for deadlock detection. So the idea is, okay, instead of pre-claiming and instead of timeouts, have just an algorithm for deadlock detection. And the idea is, okay, we use a short timeout, and after the timeout, we do not abort the transactions, but then we are looking for a deadlock. Okay, so that's a hybrid approach. And and how to find cycles in a directed graph. So the idea is, okay, we just start at one node, and then we see all the nodes which are reachable from that. So we do a depth first search, and then if we all meet a marked node, then we know we have a cycle. And the idea is, okay, this depends on the number of nodes which is equal to n, and the number of vertices which is equal to m. So we have n plus m linear complexity. Okay, so yeah, there's also an algorithm presented here, and the idea is, okay, we just with any topological ordering, like we have transactions A, B, and C, and D, not transactions, but we have resources A, B, C, and D, and we say, okay, just do any topological ordering, like A, B, C, D. So that's what we do. So that's the topological ordering. So actually I should not use an arrows here. I should use, I should use the smaller symbol, T, T, T. Okay, and then the idea is, okay, let's add restrictions. So we want to know, okay, we have a certain restriction that B comes before A, and then, okay, let's check. So in the case that our arbitrary topological ordering might be already in this result. So if instead of A comes before B, we would have, okay, B comes before A, then we say, okay, our restriction is equal to the arbitrary topological ordering, and we say, okay, it's fine, we do not have a cycle. Otherwise, okay, we want to find the cycle. So we have a marker node, and we say, okay, this means visited. So actually we have visited this node. And then we say, okay, let's see what happens if we do a depth first search, whether we find the node again, and if we do not find it, then we can say, okay, find the node, so just let me remember this marker, it should be equal to V. Okay, it's fine. So if returned, so the DFS returns false if we reach a cycle. Okay, so actually I'm not a fan of this algorithm. I try to understand it right now. DFS is equal to false means cycle. Okay, so if false, so we have a cycle. So this is actually, we have a cycle found, and therefore we cannot add this restriction. So we have a deadlock. And otherwise change the topological ordering. Okay, so actually I'm not really a fan, so I'm using the slides of another professor, and actually it should also be like, this is actually a comparison, so either this should be an equals, or this should be an assignment, so there should be 2 points here. So never mind, so it's just the example of an online cycle detection algorithm. Actually for you should know there are algorithms to detect cycles. I'm not a fan of this one because actually the notation is not the notation is not nice, so for you just know there's an online cycle detection. Yes? I'm not sure. So like the ideas again, the ideas, can we add a dependency between two resources without creating a cycle? So like we have between two transactions. So we have more than, so as you remember, we have here more than one transaction. And the idea is, okay, we start by an arbitrary order. Like say, okay, we have T1, T2, and T3. And so on. And then the idea is, okay, we want to add dependencies. For example, we want to add, now let's do plus T5 should come before T2. This should be added. Yeah, and actually that's what this means. So here we add the dependency between two transactions. Like T5 should come before T1. And then we see whether by chance our ordering is already equal to that. So if that's the case, we can say, okay, it's fine, we don't have any cycle. Otherwise, we say, okay, otherwise, let's see, look for a cycle. And then we do a search for cycle. And then we see, okay, if a cycle is found, cycle found. And otherwise, no cycle. This means we have to change the ordering. Yeah. But actually, I have my problems with the algorithm and this notation myself. So I just included it in the slides, and actually I want to focus on other topics. For you should know, there's an online cycle detection algorithm, and it's homework for you if you want to know more. So like how the slides continue is like here we show the depth first search where we have marked some nodes and whether we have and whether we reach the old one. So equals 2 means that we are already coming from the node, and if we are coming to a node that already has been marked, this means we have a cycle. And if this is not the case, we have to do a first search for all the children. And we do this recursively until we find a cycle or not. So marker equals 2 means we visit a node already visited. So this means node has been already visited. So this means cycle. Yeah. And so if DFS, if you return false, we know, like, it's really strange because like the negation of false is true. So if we have found a cycle, return false. So again, we have a cycle here. And here we return true if we don't have found any cycle, no cycle. So DFS actually returns true when no cycle found. Yeah. So that's actually the algorithm and the meaning of the algorithm. So it returns true when no cycle has been found, and it returns false when a cycle has been found. So it returns false when visiting a node that already has been visited. Yeah, actually the idea is, okay, apply this to a weight 4 graph and we find cycles and then we can eliminate any cycle. So that's the idea. Okay. And then the remaining functions about shift, and actually the shift here does not make many sense because like actually here this should be if marker of v is greater 0, so here we actually have b. This is only the case for b, and this is only the case for a. Yeah. And then the idea is, okay, we change the topological ordering until we have the original ordering. Yeah. Okay, so for you there are online cycle detection algorithms, and here this was a nice example. Okay, so let's talk about locking again. And the idea is, instead of locking everything, so we could say, okay, have a serial execution, lock the whole database. Good luck for closing the door. Works great. Does it? Okay, because I failed last time. Okay, so the idea is, okay, at which granularity could you lock? You could lock the whole database, you could lock the whole pages you're swapping out to disk, you can lock a single item. And the idea is to have all the stages, and this is called multi-granularity locking. Like the idea is here, you can have a lock on the whole database, so no one else can access the database. So you can say, okay, you want to write the whole database, but you can also say you also want to just edit a small record. And the idea is, okay, if we want to have a lock on a certain record, we always have to claim it from the top to the bottom. We say, okay, at first, I'm here and I want to say that I want to write anything. I want to update a record. Then I have to find my record, and then I can say, okay, here's my record I want to write. And this allows parallelization of multiple transactions. For example, if we have another transaction, and the transaction wants to read a full segment, for example. So here, another transaction, T2, says, okay, I want to read a full segment, or maybe let's read a full page. So I say, okay, I want to read a page down there, and then, okay, I read this page and I will read the whole page. So then there would be a third transaction, and the third transaction would write another record down here. It would start the same, but then maybe, for example, this is the target. This record should be so this record should be changed. So then it says, okay, I want to write something here, but then I see, okay, here's a shared lock on everything, and therefore I have to quit. And that's the idea of multi-granularity locking. Like having smaller granularities, and so we can say, okay, we have the pages, so actually the pages are the things that are swapped out from main memory on disk, and then I can say, okay, I want to change only a small record, but what I also can say, okay, I want to insert something, then I can say, okay, I want a lock on the whole database. And then no one else is allowed, and having that, a lock on the whole database, I can say, okay, I have to wait until the other have finished, and then we can avoid the phantom problem. You remember the phantom problem? If you have count of all qualifying tuples, someone has inserted a tuple, and then the count would change. And having this kind of locks would avoid the phantom problem. So here you remember, strict 2PL solves the mentioned isolation problems except the phantom problem, and now the idea is, okay, we have hierarchical locks, and then we can lock the full database system also against inserting, and then we can avoid the phantom problem. So yeah, I have shown you already the different locks. So actually these are the normal locks we have, shared and exclusive, and this both stem from multi-granularity locking. So, and now we can write a compatibility matrix. And Like we have our current lock. Shared, exclusive, intentionally shared, and intentionally exclusive. And now we request another lock. Like the same. So how is it compatible? So if we do not have any lock, we can acquire every lock. So if there's no lock, we can have exclusive rights or shared or anything. Maybe use another style, maybe use ticks. So here ticks works. Shared and shared, does it work? Yes, of course. Shared and exclusive, does it work? No. Shared and intentionally shared, you have seen, yes. And shared and intentionally exclusive does not. Exclusive and shared never works, so exclusive is never compatible with anything. Intentionally shared and shared works. Exclusive never works with someone else, and if there's intentionally shared, of course works. And that's the interesting part, if there's intentionally exclusive lock somewhere, it's possible, as we have to go down until the respective entry. And also intentional exclusive and intentional exclusive also works. So, as I've shown you before, if we have a record down at a leaf, and this is being changed, and actually the red item is somewhere else, this works. Yeah. So that's the compatibility matrix. And as I've shown you, locks are acquired top down, and they are released bottom up. And here's another example. Like, okay, we have here transaction 1 having intentionally exclusive, as here it writes the whole page. So this whole page is exclusive, belongs exclusively to T1. Then we have another one, intentionally shared, and we see intentionally exclusive, intentionally shared are compatible, as T2 is reading all these records, so all the records of page 2. And last but not least, we have T3. T3 is writing a whole segment, so this whole segment belongs to T3. So this is how multi-granularity locking works. Okay. And now I think the next example would be adding another lock. So if now there would be another transaction, for example transaction 4, and transaction 4 wants to write. And where does it want to write? It wants to write S3. So this is the target now of T4. So if we want to write T3, okay, we have to claim all the locks from top to bottom. So we say, okay, T4 wants intentionally exclusive. Until now it's compatible. Then we go down to the segment. T4 wants intentionally exclusive on this segment, works. But then we remember our compatibility matrix. Then we say, okay, T4 wants intentionally exclusive here, but actually T2 has a shared lock on the whole page, so the transaction has to abort. Yes. So that's how multi-granularity locking works. Okay, so that's the picture with nice colors, and here again we see it without colors. And then we have another example. The example would be T5. T5 wants to acquire intentionally shared here, actually because it wants to read S5 but the problem is T3 has a lock on the whole segment. Questions? Yes?
So it's like if you say that made in transaction, the transaction will be routed as an
If two transactions, one,
two same that made in single transaction.
it's just about. So the question is whether we have two logs in the same transaction or what?
Yeah.
But
Yeah, I understand. I wanted to know the reason of why you routed the transaction.
because T5, so currently there's T3. T3 is writing something here on this segment. So actually this would look to a schedule like we have T3 and T5. And actually T3 would say, okay, we have a write on A, and A would be located here, for example. Here would be A, then there would be a write on B. Maybe the B is located here. And then there would be T5. T5 would say, okay, I just want to read A. I just want to read A. Okay? So we see a conflict here. It's the same resource because both are located on the same page here, S5. It's actually on the page P3, but it's the same record. And yeah, so this transaction must finish. So this transaction must release its logs before T5 can acquire this. So T5 has to wait until here, free, and then there would be free exclusive of A, free of B, before T5 could log A. And the idea is, okay, to allow a more finer granularity, we say, okay, we first log the whole segment, then the pages, and then we go on to record level. That's the idea of multi-granularity locking. So in this example, T4 and T5 are blocked. We have no deadlock, as we would have to wait until one releases the logs, and therefore the idea we still need deadlock detection. So we can also use multi-granularity locking for log management. Yeah, but actually you have seen how it works. So how can we prevent the phantom problem? The idea is, okay, we can have a log for the next tuple we want to insert. PK means primary key. PK is primary key. Scans log to this tuple shared. Insert operations log it exclusively, so it's a pseudo tuple for the next tuple we want to insert. And that's one idea to prevent the phantom problem. But this would infer with concurrent inserts, as we want to have more than one insert transaction. Okay, so just to know, we have the phantom problem and we can solve it with multi-granularity locking. Okay, locking, you remember, pessimistic. And now the idea, we use timestamps, and timestamps would be optimistic. Okay, not every timestamp would be optimistic. So if I look here, okay, so it's about still with locking, but with timestamps. It's also possible. So the idea is, okay, we can still have deadlocks, and now the idea is, okay, how can we make use of timestamps to avoid deadlocks? And the idea is, okay, every transaction receives a number. and then the idea is the number is the priority. And yeah, so actually that's it. And so we have two transactions, two conflicting operations, and then we can say, okay, the operation which is executed before receives an older timestamp. So two operations, the one is executed before if the transaction with the smaller number, so actually the transaction with the smaller number executes before. So that's one idea. Okay. So actually what I want to show you is wound wait and wait die. So I have added this on the next slide. Here it's a still high level idea of timestamps. So we have the timestamps somewhere stored separately. But the idea is, okay, we have two transactions. Every transaction has a priority, and the one with the higher priority executes first. That's the idea. But then is the problem, how can we assign priorities to transactions? And if we have a low priority of our transaction, it does not matter when it will be executed. As soon as there's one transaction with a higher priority, the other transaction wins, and the other transaction is with the lower priority is the losers. So this would mean a live log. So we have a transaction with a low priority, one with a high priority, and the one with the low priority will always lose. So this is called a live log because now the transaction is waiting for a log, but one transaction restarts again and again. So the idea is, okay, to avoid live logs, we can use the timestamps as priorities. Timestamps are uniquely and growing over time, and the idea is, okay, the timestamps we use for the transaction is when the transaction started. And the older the timestamp, the higher the priority. And the idea is there are two strategies. The one is wait die, and the other is wound wait. And the idea is wait die. So wait die are the slowly old ones, like the retired ones, and they yes, exactly. So like the old ones, they are waiting if they find another operation of hold where the log is by a younger transaction. The old transaction says, okay, we wait. So if there's an older transaction want to acquire a log from a resource that is held by a younger one, the older one says, okay, I wait. And on the other way, when there's a younger one wants to acquire a log from the older one, the younger one says, I die. So the idea is always like the relationship old transaction to young transaction. So here that's the old transaction, what the old transaction makes, and this is what the younger transaction makes. So the idea is, okay, here older transactions wait for the younger ones, whereas the younger ones, if they want to have a log which is held by a old one, it dies. The other one would be the bloody old ones, and the idea is, okay, if an old transaction, a long-running transaction, want to acquire a log which is held by a younger one, the younger one has to die. So the younger transaction has to be aborted. And on the other side, the younger one, if the younger one wants to acquire a log from a transaction which is older, the younger one waits. So for example, if we have two transactions, T1, T2, and maybe we have a write of A, then here we have a write of A, and we have a write of B, so we need a deadlock still, and then we have a write of B. So what would happen? So on the first strategy, wait die. This would mean, okay, it depends. So if T1 wait die would wait until T2 finishes. On wait die it would wait, and on wound wait T2 would be aborted, because here this is the older transaction, it's the longer running transaction, and with wound wait it would say, okay, T2 holds my lock, so I kill the other transaction in this case. Okay? On the other side, what would happen if T1 already acquired all the locks? So maybe T1 already has both locks. So if T1 acquired both locks, lock von A, lock von B. And then, okay, T2 would ask T1 for the lock, and in wait die, T2 would say, okay, the lock is held by transaction 1, I die, and it won't wait, I would wait for the other one. So this is one strategy of avoiding deadlocks using timestamps without deadlock detection. Question?
I have trouble.
It's updated, sorry. Sorry, it's not printed. If you have printed it.
Also, just for clarity, the timestamp from Ti is smaller than timestamp from T, and then which one of the two is the other one? Like, is timestamp? Does that mean the
timestamp starts with 0.
Okay.
So the idea is here T1 is the older one, like the smaller. So like the number here is the timestamp.
Okay. So the smaller timestamp is the older one.
Yes. Yeah. So it's always the same, like the first one is the older one, the second one is the younger one. The younger, the higher the timestamp. And like, so it's always the same precondition, but then either the older one waits in wait die, or the older one aborts the younger one. Okay. Another possibility would be to use the commit order. So the commit order, there's one certain approach called multi-version concurrency control, and actually it uses the commit order for the schedule. But the problem is we never know when a transaction is committing. And therefore it would be the best using the commit order for determining which transaction should be successful and which not, but it's hard to know beforehand. Okay, so limitations of timestamps doesn't avoid the phantom problem, and it might lead to false positives. So we would abort transaction although there's no deadlock, and every read operation is implicitly a write, as we handle them in the same way. As soon as we read a tuple, we update the timestamp. But it's easy to distribute and parallelize, and can be extended to arbitrary number of items. Okay, so these are all about pessimistic. So we still have locks. So as you have seen, also in wait die and won't wait, we are also requiring locks, and we are waiting, or either otherwise we are eliminating transactions. So we still have locks here with these kind of timestamps. Locks with timestamps, locks pessimistic. And the idea is, okay, instead of having pessimistic approaches, let's have snapshot isolation. Snapshot isolation is an optimistic approach. So at the beginning we do nothing. At the beginning we just do what we do, and at the end we check. And the idea of snapshot isolation is, okay, what is a snapshot? You should know, like making a photo. And you say, okay, I make a photo beforehand, I make a photo afterwards. And afterwards I compare it, whether anything has changed in between my transaction. And then the idea is, okay, I have my two snapshots, and then I compare whether something has changed, and if it's not the case, I can commit. And that's why it's called snapshot isolation. And the idea is, okay, if I make a snapshot, what do I see? The whole data, exactly. So yeah, it's the whole data, but only two writes. So I've seen what is written on disk. So I see the current state of the disk. So what I can't see using snapshot isolation is whether someone reads the data, if there's another one also reading the data. And that's the downside. So the idea is, okay, of snapshot isolation, what I actually do is I have the transaction. Now it's, yeah. So I have the write set of my transaction, of one transaction, and I compare it to the write set of another transaction. Of another transaction. And I show whether this has changed. So before writing down my changes to disk, I compare whether what I would write down to disk has been modified by someone else. So actually what I do is I'm comparing the write set of my transaction to all the other write sets. And if this is equal to nothing, if this is the empty set, I'm allowed to read. And that's actually snapshot isolation. Yeah. So actually only of those we are trying to change. So the idea is, like, we have a buffer where we annotate all the changes we made and we compare just them. So we can say, of course, it applies to everything, to the whole data set, but actually we just have a look onto the changed elements. So we have like a buffer where we write down all the changed elements and we compare whether there's a change on these pages internally. Yes, of course.
But we can, instead of snapshotting the whole data, we can have like a timestamp and just compare with the timestamp. Isn't that working?
Yes, it is working. Yeah, sure, yeah. But you still should know which tuples have been modified since then. So because then you have to compare the timestamps of every single tuple, you know. So the idea is you only want... Yeah. So the idea is, okay, we have two transactions. For example, we have one transaction, T1. T1 has written A and B. And B, and then before writing it down, I of course will see whether these tuples have been modified or not. And for these tuples, I can do it with timestamps. Yes, indeed. Yes, sure. Okay, what else is on this slide? Yeah, so actually it's like just tracking all the tuples that have changed. You can use the logging. Every page contains the log sequence number and then it indicates the last change. pages with an older LSN can be read safely, and for pages of newer LSN the log is checked to eliminate recent changes. But of course you can do it with timestamps. And the idea is, okay, no need for read logs. You do not need any logs actually with snapshot isolation. Read operations never wait. As I said, it's an optimistic approach. And you have serializability, as you only have the commit points, so you take the commit points at the end. So as you remember, and now I understand the relationship to the commit order, like if you do not have any logs, you have the ordering at the end. Like the ordering when you do the commit at the end, you have atomically check whether the write set of my transaction doesn't compete with any other write set. So you take the commit order, you check it, and write it down at the commit order. And therefore, you have the serializability as you have the commit ordering. So at the commit, the transaction finishes or not. If it does not finish, it will be aborted. So you have the serializability by the commit ordering, yes, and therefore it's great. Limitations, only safe for read-only transactions. And so the more write transactions you have, the more likely the chances that you need to abort one transaction. And still many systems use snapshot isolation. So actually, there's also another one. So snapshot isolation, as I told you, means you compare the write set of your transaction with the write set of all the other transactions. And there's another approach, just optimistic synchronization. And actually what you do here is you compare your write set not only to the write set of the others, but also to the read sets of the others. I can do it also using timestamps. As soon as one transaction reads a tuple, you have to add the timestamp to the tuple, and then you see whether you are modifying a tuple that would be part of another write set. So even if you have, for example, two transactions, T1 and T2, and for example the one reads A, for example because it calculates a sum, reads B and writes it down, and the other one is writing B, and then you see you have an empty intersect. So the write set of T2 is actually only B, and the write set of T1 is actually only C. So with snapshot isolation, you only see two different tuples which have been modified. So you have actually like T1 has only C, the write set, T2 has only B. So the intersect would be empty. But actually the read set, if you now compare the read set of T1, would be much larger, A, B, C, and the other one would still be the write set B, and then you would have a non-empty intersect. And this would be the case. So you see, if you remember the phantom problem, like when you add a tuple, and we have also an example with the doctors on duty. This means, like the doctors on duty example is, like there should be always one doctor in the hospital. And then this doctor says, okay, we always have to assure that this should be, for example, 1. And then there are two doctors, and both say, okay, I'm going home, another one going home. I have checked whether the others are still here, and then I write, okay, I'm going home. but in the meantime this one is also going home, and therefore both would change their own status, so they have an empty intersect for the write set, but actually all other the read set with the write set would interlap. And that's the idea. Okay, so both are reading both, but so you see the phantom problem is not solved by a snapshot isolation, but by optimistic synchronization. So here only optimistic synchronization solves the phantom problem. Okay? We have an exercise on that to better understand it next week. Okay, last but not least, we can classify all the synchronizations, what we have seen to sum up. So, the idea is we have pessimistic and optimistic. Synchronization can be either pessimistic or optimistic. And then pessimistic is always with locking. So actually on my on my sheet it would be either timestamps or using logs. Okay. Online, I changed it today. I'm sorry. And with logs. Ah, okay, so then you can't find it. Sorry. So I just wanted to have an empty slide for my drawings. So I added 2 slides 2 hours ago, because I wanted to draw. So locking would mean the two-phase locking or the strict two-phase locking, and then one idea would be the multi-granularity locking. And optimistic would be either real optimistic or using snapshot isolation. Yeah. I wanted to show you this kind of classification. If I would have the big beamer in the big lecture hall, I could freeze the slide and put it on the other one, but it's not possible here. So I'm sorry, and I also want to have the classification of the deadlock detection. And how can we classify it? We can classify it either into pre-claiming using timestamps, this would be either wound weight, so the bloody old ones, or weight die. These are the slow old ones. Or using a weight foregraph. Okay. The weights forecast. No, the left one, pre-claiming. Okay, so actually that's it for today. So I have finished with the first chapter. So, questions? Yeah.
I have a question. For page 145, times
100?
next page. Times 26. 5 times 16. 100.
This one?
Times 26. 41. Sorry, 141.
It's 124 or 21.
This one. In the PDF. Yes. The other one? The next. Next one. Yeah. Here. So now we have two the sections, TJ and T1.
Yeah.
TR. So during when you explain it, is that we have TJ which already has a lock. Does it have all the locks or only a single one?
Single one.
Single one. Okay. So let's suppose. Can you suppose that it holds all the locks?
Okay.
Okay. And then TI, which is we said that it is older because we have a relationship with die.
So which one is holding all the locks?
TJ.
TJ. So TJ has a lock on A, for example, on B.
So those are the only two ones.
Okay, and now TI wants a lock.
Yes.
Yes.
So this other relationship, TI, is older.
TI is the older one. Yes,
So
okay. So let's.
But shouldn't the older one have all the locks before the younger ones?
So let's take a number 1 and 2. So this is the older one. Okay. And
During prioritization,
we don't have. So the prioritization is not like pre-claiming. We're not giving the locks beforehand. So like the prioritization means we have to decide now. At this point we have to decide. So at this point we say, okay, what happens? And then we have the two strategies. Wait die means so the first one is the older one, the second one is the younger. So Ti is the older one, so it means wait die, it waits. So here with wait die it would wait. So like take numbers, so let's just call it VD and VV, WW and WD. So WW and WD. So with WD this means it waits. So this is the older one. And this is the younger one. And with WW, this one would be aborted. Understandable? Yes?
With WD, the abortion takes place after a arbitrary runtime, or
No, directly after the first one wants to acquire the lock.
but it waits? No? You say it waits, but also otherwise it works?
Sorry? No. It's Sorry, again, can you please repeat your question?
WD, right? Wait die.
Yeah.
It says TI, so in this case, I don't know.
Okay, so with WD, so wait die, sorry, no transaction would be aborted in this case.
Because it waits.
Because this one waits.
But then it also says in the definition, otherwise abort.
It would be the-
here. Like there, the TJ is the older one, and in this one, the TJ is the younger one.
If it says TI twice, right? TI waits, otherwise abort TI. So if it doesn't wait, you abort. So,
This is
But
wrong,
only
right?
if TS, the timestamp of
The
TI
timestamp of TI is smaller, the older one waits.
TJ, he's right. Yes,
Yeah,
right.
it's a mistake, yes. Yes, this must be the J. So T, oh me. Hmm? No, it's correct.
No, now it's correct. What?
TI waits if it is the younger one. No, it's correct, it's correct. Yeah, it's correct, it's correct, it's correct. Yeah, yes, it's correct.
Okay, but it's so weak. Okay.
Yes, it's correct, because the younger one should abort if it's the older one. The younger one should abort if it acquires a lock which is held by an older one. Yes, of course, it's correct. Yeah, that's correct. Yeah, it's correct. It would be another example we would make. So we would have another one like T2, T1, and then we would have
Wait. But no, but in this, it's like it says TS, like the TI in there is like the older one, right? So it would be the older one waits.
now the
And-
TI is only the older one. The TI only waits if it's the older one. If it's the younger one, it gets aborted.
But DJ
This
is
is-
the younger one. But he
Yeah.
already has the
Yeah.
law. Why should it wait? You can do whatever you want.
I think you should finish the second drawing because I now
Yeah.
understand it. So there's two scenarios. It can be the older one requesting or the younger one.
Yeah,
The
but
older
the
one
younger
requests-
one already has it. Why should we request it again?
Yeah, because
then
like it's the
both-
wait die
In
strategy.
theory, in this scenario, yes, but there's also the other scenario, right? Where the younger one asks for the lock from the older one, and then it aborts.
Yes, but let's keep it wait and die.
Yes, it is wait and die.
Yeah.
It also aborts.
Yes.
In wait and die, it can abort with
So
the
which
younger
one?
one.
I or A? Which of the transactions?
The younger one aborts, the older one
Why
waits.
should the younger one abort?
To avoid a deadlock, because like the older one should finish, like otherwise. So let's make the other example. Like the idea is let's
Why not only switch the header of the upper graphic?
so you mean actually this one. I switched the below one. Log von B and then log of A. What happens? Yeah, exactly. Yeah. With wait die, so now this is the younger one. And this one wants to acquire a log held by T1. And then with wait die, this one would be aborted. And with wound wait, it would wait. Yes. No, it would wait.
What is the younger one?
The younger one.
Who is the younger one? The younger
So it's
one
always like
aborts
here.
with would wait.
No, only if an older one wants to acquire a log held by a younger one. Then the younger one has to abort, but it waits otherwise.
It only depends on the
Yes, that's the idea of timestamp based deadlocked.
Yes, but T1 is the older one. And so the if is successful. If T1 is the timestamp of T1 is smaller than the timestamp of T2. That's what we say.
Yeah, but
And
T1 does not.
Tj aborts, and Tj is the T2 in our case.
No. So, like we have the precondition does not hold. Like currently it's if the timestamp, so we're into this case. So we now check whether the timestamp of T2 is smaller than 1. This is false. So what happens?
Okay, the first line is important. Assume Tj holds load and I claims it.
Yes.
In the second case, T1 is equivalent to Tj and T2 is Ti. And in the other example, it's vice versa.
Yes.
That's a little bit confusing.
It wasn't me who proposed this example, Ti and Tj, but yeah. Good. So we have here would be younger one would be Ti. And
No, Ti is the one that claims the lock.
okay.
We have two
Mhm.
parameters of the transaction, which is the
Yeah,
younger
Tj
and
holds the lock,
older
yes.
one. This
Yeah.
is the 1 and 2 in
Yeah.
our red circles. And we got this younger and the older one, and we got which weights and
Yeah.
which hold a lot and which weights a lot.
Yeah. Hmm?
Based on the third one, we say that Tj evolves.
Based on what? Sorry.
Yeah, the definition.
The definition of wound weight.
Yes. So then Tj should evolve, as Tj is T1, next Tj.
Okay.
That's the definition.
So the two different. So we have Tj holds the lock. Ti claims it. So according to wound weight, if what is it? So if Ti is the older one, Ti isn't the older one, so the first case does not hold. So Ti, which is T2, waits. So here it waits. And on wait die, the younger one dies, so it is aborted. Yes. Okay. Let's make a break. 15 minutes. Or 15 minutes or less. Make 15 minutes. It's fine. So we see us again in now the 1740, so it would be 55.